So the vector is a section of a line with the beginning, direction, and magnitude. Yes, size, magnitude. And why do we use vectors? First, because mathematicians love them. Love to torture other people. But in fact, vectors are presented to the math in order to represent the real life forces, yes, forces, fields. Like if the river flows, on each molecule we can assign direction and speed. And this is the vector field of the river flow. So first is physics, then is math. However, in the modern school, these things are inversed. So math is pushed on first place, and the physics behind on the second or third place. That's why people, when they graduate from the school, they barely know nothing. Because there is no connection between the real life and what they study. And here in engineering school, we are trying to put the things in place, but with moderate success. And how do we describe vectors? We describe them in most popular coordinate system called Cartesian coordinate system, in Bulgarian, Descartes, and in Latin, Cartesian coordinate system. Well, the popular notation is vector is typed in bold. Quite often, this notation is also used. Let's say vector A or vector A or A. On the books, bold font is used to describe vectors. When you handwrite it, put arrows or dashes because bold is not well documented. And to describe a vector, we need a set of three. How these vectors are called?
Components.
Basis or unit vectors, each for one of the coordinate axis, and we have three numbers: component on x, component on y, component on z direction. And if we make a root mean square, we get the module or the size, dimension, the length of this of our vector. Easy. And what else we miss to describe a vector? A, let's say, AI, AJ, and AK. What else we do miss?
Starting point. However, we can place our coordinate system wherever we want.
Yes, but to describe a vector.
Here, what operations we can do?
Direction. Direction. Who said direction? Good. We miss direction. And how to determine the direction of the vector if we know these three? That's how. So if we know the coordinates of the vector, ax, y, az, our vector is completely determined. We know the magnitude and we know the angle of direction of this vector. And which computer program we can use to solve this, because if I give it you the numbers, no way that person can solve it without one or two mistakes. So that's why we use, for example, MATLAB in order to run these calculations, and eventually we'll see why this is useful for other things also. So, here is an example. A force exerted on a point with components on x, y, and z, minus 3, 4, and minus 12. We describe the force as a vector. For instance, we have a point and we simply pull it in a specific coordinate system. If we pull it, we have these components on x, y, and z. And first, we can deliver the overall force. The magnitude that we pull. And then we can determine the direction of this force. That's how the mechanics emerged as science. And eventually, smart people not only decided but discovered that we can not only add and subtract vectors, because these forces are addable and subtractable. So if you have this one, exert on a certain point this force, and you exert the opposing force with minus, the sum of these two forces will cancel each other. Zero, yes. And this is easily proven if you add to this something for force minus F, which will be minus 3i, minus 4j, and plus 12k. They will cancel each other, and this is the mathematical proof that forces can cancel each other. So this is the basic operations that we can do with the force. We can multiply it. If you double F will be double 3, double 4, double 12. If you have double the force. Direction will be the same though. So this is simple calculations that we can do with vectors. But people, smart people, really smart people, not average smart people like us, invented that we can do a bit more with the vectors. And one of these things that the math teacher in, it was called in Bulgaria, selected chapters in mathematics, which was kind of a part 3 of the calculus in English. tortured us with scalar or dot product, vector or cross product, or triple scalar product. And there were theorems to prove, things to solve, and the only motivation behind was, Peter, if you don't solve it, you will fail on exam and go home. Because in the good old days, if you don't take maximum 2 exams within the semester, you pack your stuff and quit the university. Now you can take 2 exams in your time of study and still be considered a student. But at the time when I was a student, that was the rule. No more 2 exams for no more than 1 year. And math was one of the kind of a deadly subjects that made the selection between. And because the teacher forces us to study this, but not explain why we do study this, it was particularly painful. I will try to give a hint why do we study that. So first of all, what is the scalar product of 2 vectors?
Is the projection of one of the vectors on the other?
Exactly, that's what actually it is. Very good answer. Apparently you studied the math well. So this is the projection of one vector over the another. It's the notation. Notation is the way we describe the operation. Is a large dot. This is not a simple multiplication dot. It's a scalar dot. B. A dot B. That's how it is denoted. And the math operation behind is the module of vector A times module of vector B times cosine of the angle between these 2 vectors. And if you have the coordinates of the vectors, in MATLAB you can really easily perform this operation. So, multiply the x components, y components, and z components, and you're done. You calculate the scalar product or dot product. And as the colleague said, this is the projection of A vector over the B vector. And you can see the immediate relation. If the A vector is orthogonal to B, this dot product is 0. And if these 2 vectors are in line, then what? We have the maximum of their.
When they're perpendicular.
If they're perpendicular, 0. If they're in line, maximum. This is called scalar product of 2 vectors. The next, even more sophisticated torture. It's the cross product. Cross product is A cross B, or called also the vector multiplication of 2 vectors, is A magnitude of vector A times magnitude of vector B times sine of the angle between them times unit vector which is orthogonal to these 2 vectors. which doesn't make sense a lot, right? But it is what it is. So if you have this edge here, and here you have vector A, and here you have vector B, the vector product, the cross product, will point in this direction. That's how it is calculated. The unit vector orthogonal to the plane of these two vectors. And if you have MATLAB, you simply solve this determinant. And you will get the direction, the product of these vectors. How this is solved? Very easy. It will be A times, this times this minus this times this vector A, this times this minus this times this vector J, and this times this minus this times this vector K. This is how the easy, as you say. And here how we describe it: vector A, vector B, angle between them, and this is the result. The result is an Indian arrow. You know Winnetou, have you read it? The Prime Minister read Winnetou also. Where you launch the arrow and you watch behind it, you see the feathers.
The cross section.
Yes, and the feathers means that the arrow goes from us toward the screen. The reverse thing, this is very popular in books. You will see this notation means the arrow goes from us toward the book. And if you see this, means the arrow goes from book to us. This is very important. So how much will be the rotation or the cross product of the vector? Sorry, not the rotation, the cross product. If the vectors are orthogonal,
1. Maximum?
I think
oh yes, you're right, maximum. And if they're in parallel, it will be 0. Yes, you're right. Sir. And that's how, a simple example, A vector 2 minus 2, 1, B vector 3, 4, 12. And here, the cross product, let's say C vector equals A cross B. It will be minus 20A, minus 21J, plus 14K. And if you plot it, you will see that this result is orthogonal to these two vectors. So up to now, this is solely mathematical operation, which doesn't make a lot of sense. But here is the example. Let F is the vector of constant force exerted over a point which moves on a path L. What does it mean? This is, let's say, straight path L. And we have a point which moves, and we have a force F. So, work which is a scalar value, will be equal to F dot L. When the force will make the most of the work.
And it's in line with the direction.
The direction of the movement of the point, exactly. And if the force is orthogonal to the path,
There will be no movement.
no work. It could be movement, but due to another force, not due to this one. So on this point, there could be, we can divide this force as Fx and Fy. And Fx will be in line with the path, and Fy will be orthogonal to the path. And the sum work will be sum of cross products of dot products of Fx dot L and Fy dot L. But Fy dot L is 0 because forces is orthogonal to the path. So this won't do any work, this component. That's why we use the dot product. Now it becomes a bit more clear why these operations were introduced to the physics, because there is a great benefit out of them. And how about the cross product? Here is what. We have a conductor, and current is flowing through this conductor. And we put them on magnetic field, constant magnetic field. What will immediately happen?
The conductor will feel a force.
Exactly. The conductor will feel a force. And this force, how we determine it?
With the rule of right hand.
Yes, if we put the hand, so the current is with direction of the thumb, and the magnetic field is with direction of the index finger, the force will be with the direction of the palm. And basically, this will be B cross I, the current. So this is where the cross product takes place. What will happen if we reverse direction of the current?
The force will be the opposite direction.
Exactly. The force will emerge from the screen
Come towards us.
towards us. And third thing, what if the force, the field is in line with the current? There will be no force on the conductor. And this is typical example of the cross product of vectors. So in physics, we use math to describe physical events, physical things. In math, they simply manipulate and sometimes math is apparatus. It's a approach to solve problems. Math gives opportunity to deliver many solutions, but some of the solutions make sense, some of them are impossible. So, for mathematician, if you have a house and 2 people enter in the house and 3 people exit the house, how many people will be in the house? Minus one. Which, is apparently absurd, It's a valid solution. If you don't write this on an exam, you fail. But in practice, doesn't make a lot of sense. And here we go even further. So have you seen the del operator? Yes, it's consists of the derivatives over directions in the coordinate system. Nabla del operator. It's very. It has quite a lot of applications in the modern tech. For example, what gives us the del operator?
The speed.
The direction.
Good, yes. The speed is one of them.
The direction in which whatever we're taking a derivative of increases.
You're almost there. You're almost there. Great math. I sense in you. It's first of all, it is applied over a scalar function. So it works on scalar function, and one of typical scalar function is the terrain map. It associates a point with a height. So if we have a mountain, a hill and valley, we can plot it like this here. And if we apply a del operator over this scalar field, the set of points is called the field for some reason. If we apply the del operator, we will get the direction of the fastest change of the function. So basically, we will get the direction of the peak. This is the. Or if we have a case of a line, we will get the speed of a point, for instance. Okay. And now we combine del operator with dot operator. And we get so-called divergence of a vector field. What is the divergence of a vector field? First, how is it calculated? We have the del here in the first bracket, dot vector in the second bracket, and we get this, which is partial derivative of each vector component. This is how divergence of a vector field is delivered. And what will be the result?
General direction of the vector field.
The result is scalar, as we can see. It's a number.
Speed of the vector field.
Everybody gave up. So. And the next torture is the cross product, rotation or curl.
Are we doing this because of the Maxwell equation?
Yes, exactly. Otherwise, there is no explanation.
Yeah.
curl, what is curl in English?
Or
Yes.
Kudret.
Точно.
Girl with a curls hair. It
Yeah.
was actually girl with the pearls in hair, but sounds similar. If you know this sound of Omega, it was the song. Hungarian rock band. Omega. Anyway, so Nabla cross F. Here is the PQR. This could be numbers, this could be functions. Nabla and cross product. And we calculate it as a regular cross product. Directional vectors, derivatives, and the vector components. And we get this result, this thing, what will be the direction of this one? The result. What will be the direction of the result?
Perpendicular to the field.
Exactly. It will be orthogonal to the F vector. This is called rotation or curl of a vector field. And here is why we spend time to discuss the divergence. D is the electric inductance or electric field. So divergence of D equals to charge density. Divergence of B equals 0 everywhere in the space. It means B vector doesn't have sources, point sources. This is the meaning of this equation. The meaning of this, a rotation of E vector equals change of magnetic field in time. Does this make a lot of sense to you? No.
So basically, when we have magnetic field that changes in time, it creates an electric field
Which curls, exactly. This is the proper way of reading the Maxwell equation in the reverse direction. Math has identity. There is no priority in math, but in physics there is a priority. Something is cause and something is the result. And here, change of the magnetic field in time causes a curl in the electric field. Yes?
Is it relevant to the circular polarization because it rotates?
Well, in very loose meaning, yes, but in fact, this is on a level much lower than polarization itself. This is point events, point things. Math is very good in describing things in a point, not good in describing things in a whole. Like picture describes the world much better than a math as a whole, like the art. But it's very inaccurate in a specific point. Math is very accurate in a specific point, very inaccurate in general. That's why you look at the black hole and you think that, oh, there must be some curvature in space, there must be some change in the time, speed of time, but what exactly happens, nobody knows. They paint beautiful theories around, but is exactly what we write, is what actually happens, nobody knows. There was initially black holes, now white holes, then something else, theory changes every 10 years. Very good theories are plotted, but and here with electromagnetism, it's almost 100 years problem, we are almost there, but never just there. We know almost everything, but we're not quite clear what actually magnetic field is. And smart people, they saw that change of magnetic field in time causes electric field, which has a tendency to curl. This is what this equation says. And what this equation says?
Which equation?
The last one. It also must be read from the back to the beginning.
When electric current go through a conductor, it creates magnetic field.
Yes, this is the first one, the first part. And the second part is that change in the electric field in time will cause a exactly curl of the magnetic field. And this is very easily proven, like if you have a capacitor and here between plates you will have electric field. And if you apply the time varying voltage, this E field will start to change in time. And this change will cause time varying closed curve magnetic field. And what will cause this magnetic field, time varying magnetic field?
Current opposing.
Time varying magnetic field will cause
Electric current.
time varying curly electric field nearby. And what will cause this time varying electric field?
Magnetic field.
It will cause time varying curly magnetic field. And then and how we call this process?
Electromagnetic wave.
Exactly.
Transmitting away.
Yes. That's how transmission of electric energy, EM energy happens. And who invented that? James Clerk. And here are some physical examples. What is this? This is a sink, kitchen sink. Here is the point where the
Sources.
source is, exactly. And that's what divergence tells us. Positive divergence, there is a source of the field.
Negative.
Positive divergence, source. Here is the area when as many molecules or field lines enter the area and the same number goes out. So So there is no sources in, and divergence is 0. And the thing where everything goes in,
Black
Div-
hole.
yeah, divergence is negative. That's how the divergence works on water. But the same is applicable to electromagnetic field. If we have charges, divergence is positive. If we don't have charges, divergence is 0. And if we have negative charges, divergence is negative. And here is a tornado. When we have laminar field, so no curl, we have
Zero curl.
zero curl, yes. And where the tornado spins, then we
It
have
depends on the direction.
yes, plus or minus depends on the direction of the curl. And here is the example with the charges. We have charge enclosed in the space, divergence equals rho, the charge density. If we go out, the number of the line forces goes in is the same as the number of line forces out, 0 divergence. For the curl, a bit more complex. We have a conductor goes through the surface and it forms magnetic lines. And here we have ability of the fields to form curly shape. That's why rotation is equals to the current flowing. If we take the curl here, it will be 0. So that's how the electromagnetic things work. And about this application towards electromagnetics, we have a coil which creates a magnetic field, and this field passes through our probe here. And if we apply a constant current, there will be a constant field, B, which will not cause anything on the ampermeter here. We will see nothing. Only the moment when we turn the current on, we will see something and then nothing. There will be a magnetic field, but it won't react with the conductor. But once we start to change the magnetic field, either by changing the current, either by moving the probe, the loop, this will cause either current if the loop is closed, either voltage on the terminals of the loop. And this is called Maxwell-Faraday equation. And as you can see, direction of reading is vice versa. The change of the magnetic field in time causes curl of the electric field. What does it mean here? It means electromotive force. What does means electromotive force? It means something forces electrons to move. And the last equation before the break, we have a capacitor here and we have a current. If the current is steady, DC, direct current, nothing will go. But if we apply a time varying harmonic current, there will be a current here, and over a closed contour, closed line, C, with area S, we will have this. The current equals to circulation of magnetic field over a line that encompasses this area. And when we'll break down to the point, we'll get the circulation, the curl of vector H of the magnetic field caused by this current equals either to the actual current due to electrons or the virtual current that flows between what? Electrodes of the capacitor. So here we have a virtual current, which the genius Maxwell called displacement current. Time varying change of the charges. It equals to current, and this can also cause circulation of magnetic field. So, any questions? Now we know the mystery of the Maxwell equations. They are foundations of electrodynamics. I can tell you that this is called theory of the field for a reason. Because not everything is proven up to 100%. That's why it is theory, like general relativity theory. Everything is pretty much clear, but almost there, not right there. Here is the same. Everything is pretty much clear, but not completely clear.
Yeah, what is the suspicion?
Hmm?
What is the suspicion? What is there?
What is there? I will give you an example. Even the very simple things are not quite clear, like magnetic field. I will give you a very interesting example to think, and maybe one of you can solve it.
Maybe.
Here you have a conductor. And you have the electrons inside the conductor. And they will exert the field. The field is a force, minus. They will exert the force over a charge, right? And what will be that force? Electric force.
Mm.
And if these electrons start to move, they will start to exert a magnetic force over a current.
Mm.
So we have two different forces. But if you look other way, let's let's say, we also have positive charges. And if nothing moves, these two neutralize. Okay. Right. And if we put the current to flow, what will happen? The positive charge stays in place, and negative charges start to move. Right? And if an object starts to move, what will happen with his dimension if direction of the movement? Exactly.
Length contraction.
It will shrink because of the relativity theory.
Mm-hmm.
And if it shrinks, what will happen with the charge density?
Increase.
It will increase. And if it increases, it will start to exert more negative force than positive force. And that's why it will occur to us like pulling us toward the conductor. So basically, according to this point of view, there is no magnetic force. There is only electric force, but under general relativity, which contradicts to the Maxwell equations. So, as you can see, even with very simple example, you start to see the gaps in the theory, you know. Yes.
But since the electrons, they will shrink, but the distance between the positive charge will.
No, it will be constant, you know, because you observer that doesn't move. But if you start to move, then the positive charges will shrink, and then you see a force opposing to the what you have seen if you are not in motion. So actually, the field will change the direction, which also doesn't make sense, you know. The field can be either one way or another way. But combining these two theories, you will see that actually field depends on the point of the observer or the status of the observer.
So according to this.
So the things are a little bit more complicated than we are simply describing them here. Or they are valid only in our portion of the universe, in our constant position. If we don't move and we don't blink or breathe, we see something that we describe very well. But if we do something, then the theory is no longer valid. And that's why it's called theory of the field, not facts about the Yes?
So according to this idea, there is no such thing as magnetic field, it's just electric field.
Yes. And it makes sense, you know, if you think a bit more, you start to see more and more sense into that.
So it's like illusion to us.
Exactly.
It's like
exactly.
gravity, right?
Yeah.
It's curvature of space or is it a force?
Exactly like
It's
the
like
gravity.
magnetic
No,
field.
either you fall or you don't fall or pop out, depends on the how the mass curves the space. Or the time. If you are nearby a mass, your time runs slow compared to observer which is far away from you. Which also doesn't make a lot of sense to me, but actually that's how the universe works.
I think personally it could have some idea or relevant to the behavior of gravity on the microscale or the quantum scale. Because it's like, as you mentioned, it's like illusion. So the magnetic field here, it's an illusion also. So there is some kind of similarity.
Yes, that's what we see in everyday's life. But what we see is not what actually happens. You know, it happens something in a bigger scale, and we see just here. And the map describes only one point of this.
Yeah.
And we actually don't have a lot of a clue what is how the world works. So that's the result. We're very good in creating very small, insignificant things. You know?
Yeah.
All right. Bye. Any other questions?